All right, a common question asked in AP Physics involving capacitors deals with changing the plate separation and inserting dielectrics in cases where the capacitor is connected and not connected to power. So the first question deals with doubling the plate separation of a capacitor from D to 2D. Part A says the capacitor is still connected to the battery when this happens, and it asks for the new electric field and the energy stored in terms of the original field and energy stored. And then in part B, the capacitor is fully charged again and then removed from power, and it asks for the electric field and the energy stored in this case. In the first case, the plate separation of the capacitor is doubled while the capacitor is still connected to power. Now, because the battery is what's providing the potential difference across the capacitor V, no matter what happens in this case, the battery voltage is going to stay the same. Now the question asks about what happens if the plate separation were doubled after the capacitor was removed from power. So in this case, there's no more connection to the battery, so the voltage can change. But now the charge on the plates has nowhere to go, so when there's no battery connected, the charge on the plates is going to stay the same. Okay, so the capacitance of a capacitor is given by capacitance C is permittivity of air epsilon sub 0 times area. Neither of those are changing here, over the distance between the plates. So in this case, the distance between the plates is doubling, which means that the new capacitance is going to be 1/2 the original capacitance. It's similar for charge. The charge on the plates is given by capacitance times voltage. In this case, voltage stays the same, and capacitance is going to half. So the new charge is half the original charge. When it comes to calculating the new energy stored here, so U is 1/2 CV squared. The voltage here stays the same, but the capacitance is going to half. So again, the energy will also half. And then finally, the electric field is given by the charge on each plate over the area of the plates times epsilon sub 0. And here, the only variable changing is the charge, which is halved. So the new electric field is half the original electric field. Next, the capacitor is fully charged again, and then the battery is removed. In this case, the charge has nowhere to go, so the charge on each plate, Q, will stay the same, and all the other variables can change. For capacitance, that again will half when the plate separation is doubled. However, in this case, it's the charge that stays the same. So if I want the charge to stay the same, but the capacitance is going to half, that means I need to have twice the voltage to keep that charge value the same. So the new voltage will be twice the original voltage. When it comes to energy, I have half the original capacitance, but twice the voltage. So the new energy stored will be 1/2 times half the original capacitance times twice the original voltage. And if the original voltage is 1/2 CV squared, here I would get CV squared. So the new energy stored is actually twice the original energy stored after the plates are pulled apart. Last, just to look at electric field. Neither the permittivity of the air between the plates or the area changed. The charge, as stated earlier, stays the same, so the electric field is unchanged in this case. So pulling the plates apart of the isolated capacitor increased the energy stored. That's because opposite charges near each other have a negative potential energy because they're electrostatically bound. If I wanted to take one of two oppositely charged plates and move it far away, where U is 0, that motion would involve positive work. So separating the plates would involve positive work. That positive work is going to increase the potential energy stored in the capacitor. Example B is asking about the same thing, what happens to the electric field between the plates and the energy stored in the plates. In this case, it's when a dielectric with a dielectric constant of 2 is inserted between the plates of the capacitor. Part A, again, is going to look at when this happens, when the capacitor is still connected to power. And then in part B, the capacitor is fully charged and then removed from power, and then the dielectric is inserted. So what inserting a dielectric does is it's going to change the space in between the plates of the capacitor. So when there's just air or a vacuum there, the permittivity there is epsilon sub 0, which is vacuum permittivity. What a dielectric does is it increases that permittivity by a factor of kappa, the dielectric constant. So here the permittivity will increase to 2 times epsilon sub 0, which means that the dielectric can hold that field better, so you can store more charge on the plates, and the plates can be closer together without having dielectric breakdown. Dielectric breakdown is when charge jumps from one plate of the capacitor to the other. When it comes to the formulas, where kappa goes, anywhere there's an epsilon sub 0 in the formula, the dielectric constant kappa can be added. So in this case, that's 2. So what kappa did to the capacitance is it doubled it. So the new capacitance is double the original capacitance. And then it's still connected to power here when the dielectric is inserted. So in that case, the voltage V stays the same. So to find the new charge, with the battery still connected, voltage stays the same. Because capacitance doubles, that means the charge stored on each plate can now double. When it comes to the energy stored, that's 1/2 CV squared. Voltage stays the same because it's still connected to power. Capacitance doubled, and what that means is inserting the dielectric allows the charge stored to double as well. For the electric field in this case, which is given by the charge over the area times epsilon sub 0 times the dielectric, the charge we know doubles. However, the electric field is not going to double because of the kappa down here. The permittivity increases. So if kappa is 2, we have twice the charge over twice the permittivity. The electric field here actually stays the same. All right, so inserting the dielectric allowed more charge to be stored between the plates, but it didn't change the electric field. So the oppositely charged plates creates an electric field, and then obviously more charge should lead to a stronger field. But what happens in the dielectric is, even though it's an insulator, it's still going to polarize a little bit, which means the dielectric will create its own opposing electric field, which keeps the overall electric field the same, but now more energy can be stored there. In the last part here, the capacitor is fully charged, and the dielectric is inserted after the battery is removed. In this case, the charge on the plates has nowhere to go, so the charge will remain the same, and then everything else can change. So when it comes to the variables, the dielectric constant of 2 means that the capacitance, again, doubled to the original capacitance. And now without the battery, the charge has to stay the same. So if the capacitance is going to double in order to keep the charge the same, the voltage is going to have to half. So the new voltage is 1/2 the original voltage. When it comes to the energy stored between the plates, the capacitance is twice its original value, and the voltage, which is squared, is half. I get the new energy is 1/4 CV squared, which means that with the capacitor having a dielectric inserted with no battery made the energy go down by 1/2. For the electric field in this case, charge stays the same. The permittivity of space went up when I multiplied epsilon 0 by kappa, which means that the electric field also goes down by 1/2. All right, so in the case of plate separation, bringing the opposite charges further apart was doing positive work, which increased the energy. Here, because the dielectric polarizes, when you put the dielectric between the plates, you're bringing opposite charges close together. Bringing those opposite charges near each other is doing negative work, which then lowers the energy stored in the capacitor.